Hello. So in this video, we're going to talk about Haberman's section 4.2. And the goal of this section is to kind of interpret or derive the one-dimensional wave equation, which with a bunch of simplifying assumptions takes this form. So kind of the first thing you may notice is that so unlike the heat equation, where we have one time derivative and two spatial derivatives, the wave equation has two time derivatives as well as two spatial derivatives. Okay, so this is going to change the form of the solutions in general. But something else this is going to affect is, well, if we want to solve an initial value problem, say, right, we need to specify, say, suppose, so if we want to solve an initial value problem and we say, here's maybe the profile of the wave, the profile of our system at time 0. So we're specifying one piece of time information. Turns out that's not enough to get a well-defined solution. And so in our case, for the wave equation, we'll need to specify two pieces of information corresponding to time. And then usually what people do is specify the initial profile, or the function u at time 0, as well as the velocity of u, the velocity of the wave profile at time 0. And so once you have those two pieces of information, then you can expect to solve this and get, say, a well-defined solution. But that's all stuff that we'll talk about later on. So the motivating question is, well, how does a string vibrate? Okay. So if you take a string, tie it to two kind of fixed points, and then you displace the string and let it go. Question is, what's going to be the profile of the string as time progresses? And so we'll draw some pictures. We'll discuss this in a little bit, or here in a second. But in the end, the main tool that we'll be using is going to be Newton's law of motion in particular, okay, which takes the form, right, F equals ma. I guess I don't need a double dot there, but how does a particle or how does a body move in time? Well, you have the mass, you have the acceleration of the body. So the acceleration is essentially saying how the body's moving, multiplied by mass, and then look at the total, say, sum of forces acting on the body. And this is exactly how the particle will move in time. Okay. So our goal will be adapt this equation to the setting of a string. Okay. And what we'll see is that, well, in the end, kind of this force term involves these second derivatives in space. Where do these two time derivatives come from? Well, these two time derivatives turn out to be kind of the acceleration of the system, essentially. Okay. Okay, so let's see why that is. Okay, so here's a picture of a string. Okay, we have it tied at two ends. Our coordinate system will be, so x equals 0 is the left end, x equals L is the right end. When the string isn't perturbed or moved at all, it follows this dashed line, so that's its equilibrium position. Okay, and then you pull it up and you hold it there, and you get the orange profile. Okay. And so to analyze the system, what we're going to do is we're actually going to focus in on a little interval. Okay, do the analysis there, and then piece things together and see what happens in general. Okay. So if we zoom in on this little interval, we get something that looks like this. Okay, so right? The string continues kind of this way. The string continues that way. Okay. The equilibrium position is down here. Okay. And the string has been pulled up. It's been displaced. And so our main quantity of interest is going to be kind of the height of the string. Okay. And so we're going to call kind of the height of the string at point x, t. We're going to call that function u. Okay. So what is the height right here? Well, that's u of x comma t, what's written over there. What is the height right here? That is u of x plus delta x at time t. Okay. Okay. So how do we go about incorporating Newton's laws or Newton's law? Well, we'll need some pieces. Okay. So the second piece I actually wrote there, and it's not the horizontal displacement, but actually it's going to be the vertical displacement of the string. Okay, just the height of the string at any point, at any, or yeah, any point in space, any point in time. So it's one of the two pieces, right? But recall from Newton's law, right? Force is mass times acceleration. Okay, we're going to want the acceleration of this function u, this vertical displacement, but we also need the mass. Okay, and so for that, we're going to introduce the mass density of the string. We're going to call it rho of x. Okay, so right, what is the total mass of the segment of string from x to x plus delta x? Well, that's going to be approximately, right, your mass density, so mass per, in this case, meter or whatever unit of length we want, times unit of length. Okay, so this is mass, this is position, okay? And these are what we're going to feed in to get mass times acceleration. Okay. Why might we expect mass to play a role? Well, if you have like a piece of yarn or thin string, tie it between two ends, pluck it, let it go, it's going to vibrate fairly quickly. Okay. On the other hand, if you have something like a cable between that's like holding up a bridge, okay, or some massive sort of cable, and you displace it and let it go, it's going to oscillate a lot more slowly. Okay, so maybe higher mass means, right, the motion of the string is slower. Okay, and so that should show up in the wave equation as well. Okay, so these are the pieces we'll need. How do we put them together? Okay, so down here, right, force is mass times acceleration. What we're going to do is we're going to pretend that kind of the behavior of the string for this short segment from x to x plus delta x, we're going to pretend that we can model the behavior of all of this by the behavior of a particle, and we might visualize this particle as just sitting kind of in the middle, okay? But as written, technically this particle is going to be sitting right there because I'm saying it's the height at x. Okay. Maybe another way to say this, we're taking the entire mass of this segment of string, localizing it to a single particle. Okay. And then, well, how does this short segment of string move? It's going to be roughly how this particle right here moves. Okay. And then what we're going to do is we're going to take a limit as this short segment becomes shorter and shorter and end up with the PDE that we want to end up with. Okay. Okay, so cool. So, okay, so what is mass times acceleration in this case? Well, that's going to be, right, mass, right? Your mass density times length. So this is going to be mass. And then this acceleration term, which actually should not have these dots. But the acceleration term is just going to be the acceleration of the position of the particle, which is the second time derivative. Okay, and so that's how this second time derivative shows up. Cool. Now the question is, well, what are the forces acting on this particle? Okay. So let's go back up to the picture. So recall that, right, we're looking at the short segment of string. The string kind of continues on that way, continues on that way. Okay. So whatever force is pulling kind of this segment of string over here is going to be exactly the force, right, kind of that this segment of string out here is exerting on this segment through this point right here. Okay. What does that force look like? Well, I'm going to draw it sort of like this tangent vector, this arrow, and I'm going to call that T. So the tension at the point x plus delta x comma t. Okay, so this is the vector quantity. Okay, and it's just telling us what is the force felt by this segment of string at this point. Well, it's exactly the tension exerted by the rest of the string over here. Okay. And so likewise, we can say, well, what is the tension over here? And so for this, what I'm going to do is I'm going to draw a similar arrow for this tangent vector. Okay. Just to keep in the same kind of convention going left to right, or any, we're working with these tangent arrows, so it's a tangent to the curve. But all right, so okay, so this is going to be the arrow P of x comma t. That's the tangent tangent vector at that point of the string. What is the tension that's felt on the segment of string by what's happening over here? Well, it's not going to be this arrow, right? Because the tension isn't pushing into this segment of string. Rather, the tension is going to be pulling this way. Okay. So what I'm going to do is I'm going to change this, actually. Oops. Okay, so this is becoming a little messy. Bear with me. Okay, so the tangent vector is going to look like this annoying neon green, sort of, whatever. That's just the tangent vector at the point T of xt. What is the actual force that's being exerted? Well, that's going to be this vector, which is going to be minus T of x comma t. Okay. The minus just because instead of facing this direction, we're facing the entirely opposite direction. Okay. So these are the two forces acting on this particle, okay, coming from a string. But one of the assumptions kind of we're going to make, or that we're making, is that, well, the vertical displacement kind of the particle or of this segment of string, right, or the displacement is only vertical, right? The string's only going to move up and down. If you zoom in, look at particles and kind of the actual, material or continuum, those individual particles are only going to move up and down, and there's no horizontal motion to accompany that, right? So maybe the distinction would be, right, so take this Apple Pencil. If you fix one end and then rotate it like that, right, what has been the displacement on the tip? Well, we have some vertical displacement. We also have some horizontal displacement. Okay. In this model, we're only going to assume that if we move it by a little bit, the tip is only moved vertically. Okay. So what does this mean for us? Well, if we zoom in here, for example, Okay. This vector will have horizontal and vertical components. Okay. For us, all we want is the vertical component. Okay. So to get that vertical component, we're going to ask, well, right, what is that vertical component? So what we need to do is introduce a frame of reference. Okay. And the question is, what angle does this vector make with respect to this frame of reference? Well, the angle is going to be theta degrees. And of course, this depends on space and time. Okay. So this angle theta is what angle this tension vector makes. Okay. So the horizontal component then is going to be minus t of xt. Okay. I don't have an arrow here, so this is going to be the magnitude of the tension times sine of theta xt, right? Sine means we're taking the vertical component with respect to this angle. If we wanted the horizontal component, we'd be taking cosine of theta. Likewise, here, we can do the same thing. So this drawing maybe won't be very helpful because that's nearly flat and it's already a little skew, but we can again ask the same thing. What angle does that make? And we're evaluating at x plus delta x comma t. So the vertical component of this tension is going to be the magnitude of the tension at x plus delta x comma t times, again, sine of theta x plus delta x comma t. Okay. Okay. So what is the force acting on our particle? Well, it's going to be this plus this. So we have the force coming from the right endpoint plus the force coming from the left endpoint. And so an assumption that the book talks about is that we're working with perfectly flexible strings, which is a bit of a slightly technical maybe condition, but take it as an assumption that we're allowed to make here. Or maybe that's how this assumption manifests, whatever. So these are the forces acting on our particle coming from tension in the string. But we also want to allow for sort of black box, external forces, maybe gravity or some sort of load sitting on the string is also affecting its behavior. And so for that, we're going to add this black box term, this q of xt, which before we used for source, now we're using for a catch-all for whatever the force is. And we're going to take this as force per mass. Okay, so we're going to multiply by mass right here. Why? I mean, well, so what you could do is not include this. Just have to be careful with the units. And having the delta x here is going to simplify some of the equations later. Okay. Okay, so mass times acceleration is this term right here. Force is this term right here. So Newton's law of motion says, well, they're equal. So on the left-hand side, we have mass times acceleration. On the right-hand side, we have force. What we can do is divide by delta x, okay? Move delta x to the other side. We're going to end up with an expression like this. Okay? So that's why we wanted to have the delta x in here. But now this increment, delta x, is being associated with these vertical components of the tension. Okay? So of course, the question is, well, what if delta goes to 0? Or delta x goes to 0? Okay? Take the limit as we consider a shorter and shorter segment of string. 0 to 0 is 0. 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 0 we're going to end up with an equation like this. Okay, so again, this term remains unchanged, but this whole thing divided by delta x becomes this partial derivative, right? And so keep in mind, tension up here is at x plus delta x. The angle right here is at x plus delta x minus the tension and angle at x. And so as delta x goes to 0, we end up with d dx of t x comma t sine of theta xt plus this other term rho q. Okay, so what we would like to do is express this in terms of u, right? I mean, even better if we could express it in terms of du dx, because then we get the two x derivatives, okay? And so that's what we're going to do next. So if we assume that the string doesn't kind of vibrate too much, or if kind of the displacement is small enough, the angles that the short segments make, especially relative to each other, if these are all small, right? Or mathematically, if we assume that theta is approximately 0, well, what do we get? So if theta is approximately 0, du dx, which is going to be the slope of the height of the string, right? Because u is the height of string. Well, what is the slope of that string going to be? It's going to be, so the slope is going to be tangent of theta, right? Where theta is the angle of kind of the tangent line, right? Where you're measuring the slope. What is tangent of theta? That's sine of theta, cosine of theta. Okay. And so here we're going to use this assumption, the simplification of small angles. Theta is close to 0. Cosine theta is close to 1. Sine of theta is close to theta, which is close to sine of theta. Okay. So I guess there are a few other modifications or variations that you can do with this small angle. What's going to be most convenient for us is going to say, well, this is close to 1, doesn't really matter. So we're pretty much left with sine theta. If you want, you could ask, well, what if we make the approximation of sine of theta is approximately theta for theta small? Try it, see how it plays through. But anyways, okay. So the takeaway here is that the slope of our height, or the vertical displacement of the string, this is approximately sine theta. Okay, so what does that give us? Well, this remains unchanged, this remains unchanged, tension remains unchanged. But what's changed is we've replaced the sine theta that was once here with the du dx, right? The slope of the string. And so removing kind of this argument right here, these arguments, that argument, whatever, we get the simplified expression for the wave equation for a string if we're keeping all of the kind of physical and material properties in the equation. Particular rho, t, rho, they depend on the material. Q may depend on the material, may depend on other external forces like gravity. But otherwise, this is one form of the wave equation to keep in mind. Okay. So another assumption that the book talks about in a little more detail is this notion of being perfectly elastic. What does that mean? Well, tension only depends on kind of the local stretching. Okay. It's not so much a global force, whatever. What does it mean in practical terms for us in our development? Well, for us, that means that kind the tension at a point in space and time is approximately constant. Okay, like before with the heat equation, where we assume that kind of that diffusion coefficient, that flux term K0, that was constant, right, depending on the material of the rod. Here we're assuming that the tension is constant throughout. Okay, so what does that get us? Well, it lets us pull this kind of this tension or this T0 term. If I scroll back up here, it lets us pull this out of the derivative because it's constant, right? And so then we're left with this expression. Okay. Okay, so kind of the final thing is, well, let's talk about this term right here, okay? What if, or maybe in what situations, can we assume that this is 0, right, this q of xt? I mean, sure, we can set the function to be 0, but when physically does that make sense? Okay. So one example might be when kind of this source term or this black box force is constant. And so kind of the way I've written it here, maybe you have gravity acting on the string, right? So if you have a heavier string tied between 2 points, it's going to sag. If you have a lighter string or like a really taut string tied between 2 points, it's not necessarily going to sag. Okay. So usually this source force might be gravity, but maybe gravity is not nearly as strong as kind of the forces being exerted by tension, right? So what's being written here is the absolute magnitude of this gravitational force is significantly smaller than kind of these tension forces. Okay. So this is a situation where we can ignore Q or set Q to 0, right? So mathematically, that's what we get. And so we get that simplifying assumption. And then here, right, so this, before we had a plus rho Q, that's gone to 0. And then finally, if we divide this over there, we get d squared dt squared on its own. We write this term as c squared for many reasons, where c squared is this tension, constant tension, divided by this mass density. So if your string has a uniform mass density, rho will also be constant. And in that case, this will be constant. But otherwise, this is the form of the wave equation that we had way up top. Okay. And that's how we get the wave equation from Newton's law of motion. Stop